Hello, welcome to a processing tutorial. This is going to cover two topics. The first is sort of a review of strings, as you can see from the sketch I already have open. And the idea here is just to sort of fill in some of the background to tell you a little bit more about how strings work and some of the methods and that we can use. And the second topic is going to be on tabular data that comes in table format, which will be very useful for us in terms of data visualization. And so I'll show you two sketches there, one of which will just parse a simple text file and is more or less just an instructional sketch. But the second sketch will actually take numerical data and turn it into some graphics that you just might find familiar when we're all done. So that's the outline of what I want to do today. And as usual, I am just using the latest version of processing. I don't think I need anything else here. I'm running this recording in HD. It's in a high screen resolution, so depending on how you're viewing it, you might need to zoom in sometimes. But hopefully the code will be adequately visible. And I do encourage you, as always, to follow along in the code, pause the video when you need to, make sure you understand how to make the code work. And the only way to do that is to type and do the code yourself. Watching me doing it, while that might be satisfying and even sometimes entertaining, is not really an educational approach. So I've made myself a big mug of jasmine tea here, and I hope you have something appropriate so that we can get through today's material, which is not very advanced material, I have to say. It's a little bit should be easy for you to follow along. I do hope so. Okay. So to start with, again, the first thing I'd like to do is overview of strings in processing. And the first thing I want to point out is that a string is a class. And in fact, let me change here string to be uppercase, because the string variable type is uppercase in processing, which is a very good hint that it's a class behind the scenes. It's not a primitive data type, but what they call a composite data type. And that means that hidden away under the hood in a library built into processing, it's an object. And every time we make a string, we are instantiating an object. We're creating a new instance of an object. If you understand that, it really, really helps. So the way we access strings uses the object syntax. If we want to process strings, we use the methods on the string object. And importantly, we can't change a string itself. Strings are what's called immutable. They're unchangeable. The contents are unchangeable. So if we want to change the value of a string, we end up copying that result to a new string because the first string cannot be changed. So there you go. This should say string in uppercase. If we want to change the context of a string, we need a second string to hold the results. So here are some methods on the string that we'll use, and I won't belabor the point now. Let's just look at how they work. Change that to string. Save. So in this example, I already have all the code written ahead of time, just because it's a little bit finicky and you don't want to see me making lots of typos until the second half of the video. So everything I'm going to do with the strings, I put in a separate method. Just for convenience, there was no real need to do that in this case. And then I am saying no loop because we're not actually drawing anything to the screen. We do not need a draw loop, and we don't even need to type out our void draw function at all. So nice sip of tea there. Everything is in string stuff. And I think mostly, yeah, that's it. Okay, so I don't think I'm even using this So let me fix this up as I go. Right, so I first define a string, S, in the time-honored fashion of defining variables. And then I'm going to set its contents. Now we could have done these in the same line. It's the same thing. But I'm just splitting everything up. So first we define the variable as to its type. Next we set the contents. It's time for processing, yes. And now I'm going to modify the string in different ways. So the first thing we can do is use the method toUpperCase here. And that will give the results back to a second string because S is immutable. We cannot change it. And then I will print what that looks like. So uppercase, and then we'll see our string. When you're comparing strings, the best way to do it is to use a method called equals. So this line here takes our string S, converts it to lowercase, and then using a second string method says, is it equal to this string? It should be, because all I've done is taken its time for processing and made it lowercase. So it should be, and if so, we'll print strings are the same. Otherwise, we'll print strings are not the same, so that our window down here will contain all our output for this example. We'll see that in a moment. Now, when you're joining strings, you also need a new string to put the results in. So if I take my original string and add on get ready, the plus sign is understood as concatenation, which is a fancy word for joining. So get ready will be added to the string we had originally to make a longer string that I'm going to call result. And print that. And then finally, there's some useful string methods. So if we want to know how many characters are in the string, we've got a length method here. Sorry, highlight that for you. We have a length method. If we want to look at specific characters in the string, we can do that with char at, and then give the index number. So this I should explain this a little bit more. A string is an array also. So it's a class, it's an object that's been made for us, but the data is stored internally in an array. So we can address it as if it was an array. So the 0th, let me go up to my string. Here we go. It's time for processing. So the 0th character in this is the capital I. The second character, but the one with index 1 is the letter T. The character with index 2 is the apostrophe, and so on. So it's an array indexed from 0, just like all our other arrays we've been using. So when I ask for the character at 3, I'm asking for the 4th character from the string. And we can expect that to be S. We can expect that to be S. Similarly, we can search for characters in the string using index of. So this is essentially saying, what is the index of the character F? So where does F occur in the string? And I can also return part of the string using substring, which again takes these index values. Okay, so let's actually run this and see now. Now I'm going through this at some sort of speed because, of course, I'm expecting you can pause and rewind the video as you wish. Okay, so uppercase, it's time for processing. The strings are indeed the same. The longer string is it's time for processing get ready. The length is 25 characters. The third character was S. The letter F in 4 occurred at position 10. And if you take the substring of 10 through 13, you're getting F, O, and R as the results. So the substring here is the word for, FOR. So these are just some of the methods on the string object, on the string, and of course you can look up the rest in the reference. Very, very handy. So this code, which I'll provide, is just kind of a shortcut way of looking up some of the most basic and useful string methods, which are listed here once again for you. What I want to do is explain to you how tabular data works. And for this, I'm going to create a new sketch, and I have already a folder here called Surrealists with some data in it. I'm just going to create surrealists.pde. I mean, there's different ways, of course, of starting a new sketch. I'm going to do it this way just so that I know it's in the right folder to begin with. I'm using Windows 10 here as my operating system. If you're used to the Mac, that's super fine because everything is basically done the same way in processing. Of course, there'll be a few differences in the operating system functions I use, but that shouldn't impact anything that you need to do. So so let me get that going. Actually, I can close the other one there. So what I want to do is introduce to you how to work with tabular data. And tabular data is simply data that comes in rows and columns. And we work with those using a function called load table and the following methods: get row count, get column count, and get string. Now, of course, there are other methods on that, but these are the ones we're going to use right away. These are the methods we'll use. Just put that up there as a bit of documentation for you. And I'm going to start in my time-honored fashion by just defining a couple of colors, basic colors that we can use, just black and white in this case, just so that we have these constants available for us. And then I will create my setup function, or method if you like. So this you should be well used to by this point. Let's make the background white, and the text will be black. And I'm going to define. I'm going to print some text to the screen, so I'll just make it a reasonable size, 14 point. I don't need a stroke around it. Oops, I should say no stroke. Right, so all really, really basic. And what we're going to do is just read in the data and print it to the screen. Really simple. So I'm going to create a function called read, and then I don't need a loop. In this case, I just need this. There we go, saved. So, okay, so this is our basic framework. Everything I write now will be in this read function. And what am I reading? Let's have a look at our data. So it's a text file. And it looks like, let me make this bigger. There we go. It looks like this. So you can't see these characters, but that's a symbol that won't show up in a simple text editor. It's a tab. So there's just one character in here, as you can see when I highlight it. It's not a bunch of spaces. So this is a tab delimited file. So there are basically two types of tabular data that are very common. There's CSV, which is comma separated value. And there's TSV, which is tab separated value. And these have been around since the dawn of time. Basically, since the very beginning of what we would call digital computing. So they're very, very simple. So you can either separate the values on a line with a comma or with a tab. And I've chosen the tab format because my data already includes commas. So you can't use a character as a field delimiter if that character is part of your data, because otherwise Galesburg, Illinois, USA would look like 3 different fields, and it's not. It's one field, birthplace. So the first line here, that's another thing to note. The first line tells us our what our fields mean. So the first line in the file might be a header. It doesn't have to be. It might be a header. First line of the file might be a header. If so, it tells us what the columns contain. So it gives us some semantics, in other words. It gives us meaning so that we know how to interpret our data. So it's actually very handy if that is included, especially where the data is more complex. This is a very, very simple example I cooked up with some of my famous surrealist artists like Max Ernst, Dorothea Tanning, Hugo Ball, Leonora Carrington, and other people here. So it is their name, and then a tab, their birthplace, and then a tab, and then their birth date, just so that we've got different data of different data types here that we can use. Okay, so that's all this file is. And in many real world cases, you might have hundreds or thousands or even hundreds of thousands of lines of data, depending what you're processing. This is static data. It's not changing for the duration of this project. Next week, I'll show you some dynamic data, and we'll get into processing stuff from the internet where data does change very, very regularly and sometimes also very frequently. But for now, we're just using static data. Okay, so that's our file. And notice that I put it in a folder within my project. And when you do that, it doesn't really matter what you call the folder. Processing knows to look for any source files in this location. It will look through all the subfolders within your project folder. So you can call this your assets or your data stream or whatever is appropriate. It doesn't really matter. You can organize files as you wish, which is very handy. Okay, so I'm going to put this off here so I can keep in mind what my data is. And I'm going to show you 2 different ways that we can access this, starting with the slightly simpler one. Now, what I want to do, I've given myself a canvas of 500 by 900 pixels, and what I just want to do is print out this information. So I sort of just arbitrarily chose a canvas size that I hope will give me enough room for this amount of data. Now, that said, every time I print out a line, I need to control where it's printing to on the canvas. So I'm going to give myself a couple variables for that. And I'm going to start X at 20 pixels. And I'm going to put Y at 40 pixels. And then each line I print, I want a certain amount of space between it. And so we'll call that the leading, which is what it's called in typography, or line spacing, if you prefer. Letting is a nice simple word that otherwise isn't used, so I'm going to say 20 pixels between each line just for readability. Okay, so these values will be used in the actual graphical output. Now, how to deal with my data? Well, I already told you that load table is the magical function that we need, and it returns a type of an instance of table. So I'll just give this a name, just call it tab, I guess. Well, I could call it surrealists or artists or something like that. I'll call it surrealists because that's what's in it. It's always good to use a variable that says something to the reader. So it says in the little red error there, the function load table expects parameters like string. Yes, and I wonder what string it wants. It might want to know what file to read first. That would be obvious. And it also wants to know the format the data is in, because it will handle CSV or TSV with or without a header. So you need to tell it which of those it is. It can't guess from the contents of the file. So in the second parameter, you actually put both of those in one parameter, which is a bit weird, but you do. So header TSV, something like that. That tells processing, yes, we have a tab separated value file, and yes, we have an initial header line that's not part of the data. The header is metadata. It's data that tells us something about the other data. Right, so we have our, actually that is a lot to print out each time. Type out, I'm just gonna call it SUR, S-U-R. Right. Now I mentioned get row count. It might be a useful time to validate our data. So I'm gonna store the number of rows, and likewise, no prizes to guess that I'm going to store the number of not cows but columns. Like that. So now I know something about my data, and I'm getting kind of antsy at this point because I've yet to test or run or debug my software. The more you type, the more errors you're likely to make, and I am no exception. So I'm going to call it here for a moment and just see how many rows and columns I have. I'll just print those out and run. Okay, there's my canvas. Of course, I haven't printed to it yet. It's empty, but down here it says 10 and 3. So I have 10 rows of 3 columns each, which indeed is what I expect. So it's always good to do some sanity checks as you go. So that worked. So that appears to be reading the table, but we don't know if it's got the right information yet. So we can complete this program by simply printing our information out to the screen. So let's iterate over each row. We know how to do that. Set up a counter here, J, and so long as J is less than our number of rows, I'm going to increment J. And there we go. So, so for each row, do one row at a time. And you might now guess, so I'm going to copy and paste, that within this, we need to do the same for each column. Use the variable I for that. Something like that. So how do we get the information out of the table? Well, it turns out that there are a number of different methods for this depending on the data type. So you do need to know the type of data that's in each column of your file. Now, in our case, even though the birth date is, say, 1887, it's numerical, we can treat that like a string as well, because we're not performing any mathematical operations on that. We just want to see what it is. So I'm going to get out each column as a string. Give it some minimal name. And the method to do that is get string on our table. That's not the name of our table. That's the name of our table. Which string do we want? We give the row and column positions. And that will return that one chunk of data formatted as a string. So then let's put that on the screen using our text function. Our string at X and Y. Yeah, maybe what I'll do is I'll put these on a separate line, just each one, just to make it easy. So I will then increment the vertical position. Actually, I'll put a comment there. Whoops. And we have a variable holding how much we're going to increment. So this means actually each of the columns I'm putting on a different line, so it will be formatted differently than you see up here in the source file. And then I need probably a blank line between them here. There's probably different ways of formatting this. Well, of course there are. It depends on how you want to look at it. Get rid of all the empties here. Let's see what that looks like. Aha! That looks nice. So I formatted the data, each field on its own line, but with a blank line between each of the data rows. And that's a nice listing of our file. Of course, it's merely replicating what was in the data. This is a very trivial example just to show you the table handling. We've done no data filtering or manipulation or mapping or any of the other steps that would normally be done in a data transduction or visualization project, but it does give you a start on how to manipulate this type of data. So this is actually done at this point. This is all the code that I wanted to show you. Let me close this. I turned on the debugger there by mistake. And actually what I'm going to do is I'm going to copy and paste this. Where's it gone? It pasted it up there, didn't it? Call it Surrealists 2 for lack of imagination, which is kind of ironic given we're dealing with imaginative artists, but there you go. Here we are. Of course, you have to have the same file name as the folder. That's just a restriction of processing. That's why I did that in that way. Okay, now I want to show you a little enhancement. Basically, you can also use named variables for your fields since we do know what they mean. We have that header line, so we can set up names instead of dealing with the variables, each column data as just numeric positions, X and Y positions, row and column positions. Instead of doing that, we can deal with them by name, and it does give our program a bit more of a self-documenting facility to it. So up here, I'm going to define some information. We know our first field is the artist. And birth palace. I was born in a birth palace. No, I wasn't. I'm not sure why that's flipping back each time. Something like that. So the first column is artist, the second is birthplace, and the third will actually make it an integer this time, is called birth date, birthplace and birth date. So we can read the file the same way. I can keep this stuff in here just as a sanity check. I don't need to change anything there. So all I'm changing is how we access the data. And I'm going to use these named variables now for clarity. So because we have the named variables, we don't need the nested loop anymore. The columns we don't need to count because they're going to be known by name. So we don't need this loop at all. Get rid of that. Outdent this. And we can also use a more a slicker way of looping, and I've showed you this before. It's the object notation for looping, and it's quite different. So let me get rid of the contents here. We don't need a counter. That's the benefit. Instead, we define a variable for our row. And here's something new. It's a table row type. And it is going to iterate over all of our rows, not tab. I keep putting tab for table because I think I used that in my other example. Okay, so this is similar to object notation we've seen, but it's specific to tables. So how you read that is, for each R of type table row, loop over our table instance and all rows. So this rows function, which we haven't used until now, returns each row, and it is of type table row. So these always have to match, of course. Whatever this method returns has to match how we defined our temporary variable R. I hope that is clear. It definitely takes some getting used to, this notation, but it is pretty slick because we avoid the use of I and J completely. So we can now retrieve the name of our artist from our row, which is R, in the previous line defined. We'll still use getString as before, but now we can specify it by the column name. Again, we can only do this because our data up here had the column names in place, which is why I stressed how useful that is. Very useful. Let me just copy and paste this now. So birthplace is also a string, and it is actually birthplace. I could have copied and pasted there. Birthplace and birth date is not a string. Guess what? Get int. And it is actually not called birth date in the file. It's called date. So there we go. That's how we retrieve each column. And now we can just print them where we want them. Don't need this at all. So artist, we can print at X and Y, and then, yeah, and then we'll want to increment up Y and do this a couple more times. So let me just copy and paste to make things easy here. Yeah, something like that. And once we've done all these, I will still keep this last one for an extra space there. I'm curious as to how that works. It looks identical to before, as it should. So all this example illustrates is that we can define variables for each of our fields, retrieve them by name, paying attention to their data type, and then in our actual display code, we can actually deal with those variable names. We're not worrying about indexing by integer numbers. Really nice. I much prefer this. It's actually a little bit more code, but it's more readable code. Okay, so that's it for tabular. For this tabular data example, take a moment and make sure you've saved your code and that it runs correctly. Of course, please take advantage of the built-in help, which is opening up in a different window for me because I've got multiple windows going here doing the screencast. So here it is. Pull it over here. There it is, table row. It will give you examples. It will tell you how to do tons of stuff. Now, you don't. It's not only a matter of reading data. You can also write data. 1 second. Turn down. I think I'm slightly overloading my input here. Turn that down a bit so I don't kill your ears. You can also write data into tabular files, but I'm only going to concern myself with the reading side of that at the moment. So there we go. We're done. We're done that. Okay. So I'm going to close up this here. And that's the Surrealist done. And I'm going to move on to the last part of this lesson, which is some graphics. Let's do some graphics. The whole idea of this is to come up, the whole idea of data transduction or visualization, or sonification for that matter, is to come up with an appropriate representation of the data that tells us something about it that we didn't know before, that gives us an insight into our data set. And this is particularly necessary when our data set is otherwise hard to comprehend. So my final example is exactly that. Let me set up a new file here first. It's called unknown. Why is it called unknown? Because we don't know what the data is. Here's the data. Let's have a look at it now. In this case, it's a CSV file. If I look at that, it's going to open in the nearest spreadsheet program, which in my case is in LibreOffice. And this is what we see. Now, that's going to be kind of small on your screen. Hopefully you can zoom in if you wish. It's a lot of numbers. That's all it is. It's a lot of numbers. And they all seem to be around 0. Like plus, there's minus 1.14. They go plus a bit. Mostly they're going minus, actually. Most are negative numbers. And they're all within the range plus or minus 1, or more or less, I guess, plus or minus 2. So, okay, and there are zeros in here. That's all we know. What the heck is this? Well, there's no header line to tell us. And even if there was, look at how many columns there are here. It just seems to go on and on and on, doesn't it? So this is more typical of giant data dumps that you will get off the internet from different sources. And especially, like, I love doing stuff with astronomical data, geographical data, and so on. And wow, yeah, you get into big data files with that. And it's not always clear what these numbers mean. Now, you should... Oh, wow, some of these numbers are way bigger than 1. Okay, it's good to know, because up to 22 there. So, and yeah, wow, crazy stuff. So let me close this now. So yeah, it's obviously any data you get, you're going to have some sort of schema with it so that you can understand what the data means. Otherwise, how in the world would you proceed? But in this case, I'm sort of going to pretend that I don't know what this data is, but I want to figure it out. So I'm going to graph this data. I'm basically going to just go line by line and graph the data. And to do that, I'm going to use what we know about shapes. Okay, so probably I can start with something similar to here. Why not? Just take all this from before. I want a bigger canvas. I know that because of the huge amount of data I have. And I'm actually, on this computer, going to use the FX2D renderer because it would be smoother. I'm not using text, so why don't I just get rid of this for now? I'm going to put it on a black background. Yeah, otherwise the same. I'm going to read and then I'm not going to loop. I'm just going to put the data up in the canvas once. No animation, you know, like we'll get to that next week, I think. Yeah, we'll get to some stuff next week with data that changes. So let me get rid of this one now. So this is our new file we're working on, and I hope you can work along with me. So I'll make this, all the downloads available, of course, for you, so you have the data sets that you need. Right, so how are we going to do this? Well, we start in the same way as before. So a table, actually I better call it tab this time since I keep typing that anyway. And our data, what was our data file called? Okay, it was called CP1919.csv. And yeah, that's all I know about it. It doesn't have a header. So, yeah, let me just put that in there. And it's a comma separated value, which is the default way this reads a file. So, okay. Oh, I didn't need to, oh, I could do all this again. I will. Get row count. I will do this all again because it's really useful to know some diagnostic information, you know? Really useful. Get column count and then there, something like that. Let's see what happens when I run it. We have our black canvas, super good. Rows 80, columns 300. Okay, well that tells us something we didn't know before, right? Because we had so much data that we could have eyeballed it or we could have used the spreadsheet to figure it out, but this is quicker. So that's a lot more data. That's, what's that, 24,000 cells of data, 24,000 data points, which is not a lot really, but it certainly means that we can't handle this data in the same granular way we did when it was a list of people and their birth dates and so on that we were just looking at there. So similar to before, what I want to do, I'm going to put this on the canvas this time. I'm going to graph it because I've got 300 data points per line. I don't know how else I would deal with that except as a graph. Certainly, I'm not going to display those 300 points as numbers. And so I want some initial parameters here to handle all of that. So I need an X and a Y positions. Actually, they're going to be offsets. I'll call them offsets. So X off. And I'm going to center this on the screen. So I've got 300 columns. So if I do 1 pixel per, then I've got 300 pixels wide. So to center, I take the width minus the number of columns and divide by 2. Okay, that kind of makes sense, except divide by 2, float. Thank you. Otherwise I might be in trouble there. I would be in trouble. And for the Y offset, I'm going to do something similar. I'm going to take the height and I'm going to subtract how high each row is. How high is each row going to be? Well, that depends on my line spacing. So maybe I need to define that first. I called it leading. And I'm making it a float because all of the maths I want to be in float this time because I am doing division and so on. And you know, if you do that with integers, you get serious round off errors that result in annoying things happening. So divide by 2, right? Probably. Divide by 2 dot. Boy, is it easy to do integer division by mistake. Okay, so does that make sense? So if my leading is 5 pixels, if each row is going to take 5 pixels, then I want to multiply the number of rows I have times 5, and that is the total size of my graph. If I take the total height of the canvas, if I take that away from the total height of the canvas and divide by 2, I'll get my offset. So basically I am centering here. I'm centering. And what color will I use? How about I come up with a nice color? Do I want a nice color? Oh no, I'll just choose a gray color. Yeah, I'll just use some mid-tone gray there. Yeah, okay, that might be all I need. I know the color I can plot in. I know something about where I'm going to start with my X and Y offset. I know the space between my lines, the space between my columns. There won't be a space between my columns because I'm going to graph them as individual pixels. Yes, if I need anything else, I'll go back and put it here. But I've done this a few times now. I think that's probably all I need. So how am I going to draw a graph? Well, let's use our friend P-shape. Yeah, let's use a shape for each line. It's easy. We've done it before. It's easy. So every row will be a different shape. And where will I start? With my offset. Does that make sense? Yes, that probably makes sense. So my Y position will start here, and then we'll increment it as we go. As we go where? As we go through our rows. Yeah, I could have kept some of this stuff from my previous example, huh? Because we're traversing the data in a similar way. We're just going to do very different things with the data once we have it. Okay, something like that. So we're going to go through every row. And for each one, we're going to create a new shape. So I probably need to indicate that somehow in my comments so that it's clear what I'm going to do here. So actually what I'm going to do is, it doesn't matter where these are, but I'm going to put it closer to this so that my comment, make a shape for each row of data. There we go. Now I'm telling the reader what I'm doing. I'm not putting a comment in that just replicates the code. I assume the reader knows processing, but I am putting a comment in that says something a bit more meta about what I'm doing. That's what's important here. So yeah. So okay, let's make a shape. We have a shape. S is our shape, and we know, I hope by now, that we can create a shape. And let's begin. Begin shape, and then we can do things like set our fill color. Set our stroke color. Can even set our stroke weight, I suppose, to be really complete about this. So what's our stroke color going to be? Oh, well, we gave it a color there, didn't we? We defined C as our color. So what's our fill going to be? This is an interesting point. So we're creating a shape, but the shape itself is not going to be a closed shape. So we're not creating something like a polygon where we're going to create the vertices and then enclose the shape. We're actually going to have an open shape, just a line. And so what would the fill be in order for this to work? That's a good question to ask yourself. And when I was first doing this code, I wasn't too sure, even though the answer is kind of obvious. The fill, should I give you the answer? You can pause and think about it if you like. So the stroke color we've defined as this gray up here. But what's the fill color going to be in a shape that we don't close? Well, it has to be the same as our background so that it just draws our background color. Now that wasn't obvious to me at first, but if you don't do it this way, the results immediately tell you to do it this way. So I'm just gonna skip the error there and work away. Okay, so we've got all the characteristics of our shape, our fill, our stroke weight, those are the standard ones anyway. And now I want to draw every point on the curve. That would be the second loop that we had before, where we loop through our columns. Let me just, like so. Now what do we do for every point? Remember, we have 300 of them, right? So we're just going to put them one after another. We create a new vertex at position I plus whatever our offset is. Our offset there, remember, is to get centering working. And the Y position, what is the Y position going to be? Well, that's where we have to do something with our data. And as you recall, our data were all these numbers, plus or minus, all these floating point numbers. So what I'm going to do is take the Y position and subtract whatever the data value is. Like this. Let me scroll down a bit there for you. Okay, actually that's all we need in there, isn't it? Yeah, that's all we need. In our loop, just the one line. So we're getting the float value at Ji, similar method to what we've seen before, from our table. And I'm actually going to take the Y position and subtract that from it. Now, why not add it to it? Well, because this looks better. It really depends on your data, of course, how you need to graph it. But I tried both, and you can try both too. And this looked better. This looked just perfect, actually. Once we have all our vertices, we can just end our shape. So we come to the end of the data row. Whoops, how do I do that properly? And then we can display our shape. There we go. The only last thing we need to take care of is that every row, once we're done, we need to increment our Y value. So here where I have Y, it was set to offset to begin with, and now we need to add our appropriate leading to that. So that save our work. Okay, I hope it's clear what's going on here. What I'm basically doing is I'm combining kind of an earlier exercise where we're looking at drawing a shape just using individual vertices, which is what this is doing. The only new thing here really is where our data is coming from, and it's coming out of our tabular data set. And we're creating a new shape for each row. So each row is an open, actually, let me show you the reference for this. Each is an open curve, so end shape. Let me drag that over here. You can see, if I make this a bit bigger, it will even help, that when you use end shape, there's an optional mode, and that really is just the word close. So if you put close in here, you will close the shape. And if you don't, it's left open. In other words, just a line, a curve of some type. Their example up here shows that actually. If you draw a couple lines and then close the shape, it will automatically put in the third line of the triangle. But if you don't, it will leave that open. So check out the help, guys. Use the help all the time. And what does this look like? This unknown, whoops, doesn't look like that. I don't want to print, do I? That was anticlimactic. That's better. So some of you will understand now why I called this sketch unknown. It is the famous graphic from Unknown Pleasures by Joy Division, which is a graph of data from a pulsar that was in fact received or processed at least in a tabular data format, exactly or very similar to the one I'm using here. This is not the actual data because some PhD student decades ago has that data, and I don't know how to get the data, but it's a replica of that. So there you go. Now, what happens if you decide to close the shapes? You can see this line at the bottom, which is the closing line of the last curve, but all the others have them too. So these closing horizontal lines simply mess up. It's not wrong. It's just aesthetically less pleasing in this case. In other cases, it could actually be wrong. So let me flash the fixed one up. Hello, there it is. That just looks a bit better. And what happens when you add the data to the Y position instead? Well, you can kind of understand what's going to happen before you do it. If the data values are reversed, they're not going to overlay each other in the same way. And in fact, they overlay each other like that, which is not very appealing. Because there's a little trick here that we're actually using that I haven't been explicit about. Let me unbreak the code. And what is that trick? If you look at this, the graphical impression is of 3 dimensions. So this is what's called 2.5D because it's only an impression of 3 dimensions. We are using a 2-dimensional graphics here, but the first line, the first curve here, is done first, again, with a background of black, the same as the background. The second curve comes along, and because it has a background of black, it's going to actually cover up any of the previous line, and so on. So the very last line here, what was it, the 80th row? When it was drawn, this line, because it's filled with black, erased the curves behind it underneath this profile. And this is precisely how we see objects in the distance, of course. Those that are nearer to us obscure those, assuming they're opaque, they obscure those that are further away. So it creates this kind of mountain range effect, a fake 3D effect, which is very important. So we could not have done this if we started drawing with the bottommost shape and went up. Even though we can do that, we can access the data in any order we want, but it would not have created the same impression. So there's actually a lot going on here. There's more than meets the eye, you could say, in terms of how you make these decisions about how to portray the data. You could use color. So height here, the height factor, because some of these peaks are much bigger than others, and they sort of form maybe a pattern. Perhaps if you colored this, you would be able to see that pattern more clearly. You can use data filtering so that the values out to the side, which are kind of just small noisy values, maybe you don't need to see those at all. But all of that would change the aesthetic of this curve. And the original PhD student who came up with this for his astronomical research chose this very representation as the best way of illustrating the data to make the points he wanted to make. Now, you would need to know what this data is and what the time scale is. Like each tracing here was received at a certain time from a distant pulsar, and so on. But this should provide a useful example of how to represent tabular data. Decisions have to be made as to the graphics that you'll use, the colors, and other aesthetic characteristics. But just to reiterate that we have yet to add any animation or interactivity to this. Also, this is a static data set that does not change. So in the next video, for the next lesson, I'd like to show how you can deal with data sets from the internet that are more likely to be dynamically changing, and how you can access those in a timely fashion. There are two protocols that you need to know, JSON and XML, and we will cover those in the next unit. So in the meantime, I hope you access this code, try it yourself, try variations on it, and start experimenting with your own data sets. So thanks very much for sticking with me through the lesson. My name's Robin, and I'll see you online where we can chat about any questions you might have about this. So long for now.